Okay, here we go. So last time we were talking about equations of lines and planes. Planes specifically. We'll get to lines in a moment. Here is a nice little exercise. I think this is a wonderful little result, just because of how easy it is to use. So anyway, we'll come back to that in a second. But let's talk through what it is. If there are no y's in an equation for a plane. Now, this is easy to detect, right? Just take a look and see. Check it out. In this case, there are 0 y, right? So casual observation. Then you get a really nice geometric conclusion, that being that the plane in question is parallel to the y-axis. So this plane has to have this parallelness, as I'm trying to indicate here. So again, I think this is a wonderful little result because it's how easy, how free the information is. All you have to do is glance, right? Hardly any effort at all. You don't have to compute some such thing and see if you get a certain value or whatever. Just look, check it out. There's no y's, right? And you instantly get a geometric conclusion. So great tool to have on hand. Let's talk about why it's true. If there are no y's, like so, you got a 0 here, keeping in mind that the coefficients tell you your normal vector, right? The lack of y's means that you've got a 0 in that position for your normal vector. So we can draw a picture then of our normal vector. Here it is, our normal vector, and it has a 0 right there. Now, so what? What does that mean? Well, keeping in mind that the direction vector for the y-axis is E2, which of course has a simple formula, 0, 1, 0. Right? Pretty easy pitch that these two vectors are orthogonal. And in fact, being non-zero, perpendicular. Right? So that means that our normal vector for the plane is perpendicular to the y-axis, and then I appeal to your sense of geometry. If the normal vector is perpendicular to the y-axis, then the plane itself is parallel to the y-axis. And so again, as we had previously before, this plane and the y-axis parallel. Is everybody okay with that? Does it seem like a reasonable little argument? There are analogous results for if there are no x's in the equation or if there are no z's in the equation. And I'm sure you'd believe those results for whatever it's worth, even though they're kind of sort of, obviously believable. Think through the reasoning. It's a nice little exercise. If you want to test how comfortable you are with this reasoning, put this away, look at a clean sheet of paper, and try to produce an argument for about there being no x's and about there being no z's. Be a nice practice problem. Okay. All right. Another example. Oh, wait a second. Am I not fully? There we go. Okay. So we've got a point given, and we have a couple of planes given. And our goal here is going to be to try to find a line. Specifically, we're going to try to parameterize a line that contains the point and that is parallel to both of the given planes. Right? So the line we're looking for is going to be about like that. All right. Yes?
Sorry, going back to the previous example. So if the equation doesn't have coefficients for x and z, for instance, does that mean that the normal vector is perpendicular to the xz plane?
It sounds like you're doing two examples at the same time there. So we want to break it down to sort of one at a time. But yeah, the argument would be that if there's no x's in the equation, then you'd write down what the normal vector is, and it would be perpendicular to the x-axis. Yeah.
But if like two of them were missing, then...
Oh, if both of them are missing. Oh, okay, well then, yeah, it's perpendicular to both. Yeah, right. A nice exercise to think through. If you want to talk to me after class about exploring those possibilities, just let me know. Yeah. Okay. All right. Yeah, okay, so here we are. So we've got a point, we've got two planes. Find the parameterization of the line per the picture. So now again, remember the big picture strategy that I encourage is if you are given this and you want to prove or find this, try to work toward the middle. Work forward from what you have and kind of reverse engineer backwards from where you want to get to. So let's see here. If we have, let's see, starting with the going forward, we have two equations for these planes. But notice I can reason from what we covered last time. If I know the equations, I know the normal vectors, right? So I've got these two normal vectors. Yeah, they're pretty good. My goal is to find a line, but specifically I want to parameterize the line. And now what am I going to need in order to put together a parameterization? Well, I'm going to need this point. Okay, fine, I already have that point. No problem there. Let's set that aside. And I'm going to need this vector here that's parallel to the line. So rather than doing the question as stated, it's a much more immediate question to say, I know these two vectors, and I want to find that vector. And again, looking at the picture, if you think about it, these two vectors are perpendicular to these two planes. Each of these planes is parallel to the line, which is parallel to the vector. You put that all together, and this green vector needs to be perpendicular to both of these input vectors. And again, we have a magic tool for that, and the magic tool is the cross product. And then it's all over. Is everybody on board with that one? Okay. So now, both of the previous examples that I just did, there is a tricky bit that I'm going to call a transitivity. And I don't want to be too precise about exactly what are all the different versions of geometric transitivities. But what I mean is sort of connecting dots. So if you look back at this example here, and let me clean it up. I'll get rid of the mess. There we go. Okay, so I argued that, let's see here. So the plane is perpendicular to the normal vector, and the normal vector is perpendicular to the y-axis, and then you kind of connect the dot. If this is perpendicular to that and that's perpendicular to this, then I argued that altogether this must be parallel to that, right? So that's the term transitivity. It's a term that we use to refer to things that, where you're kind of connecting the dots like that. So here's another transitivity of sorts. I argued that these vectors are perpendicular to these planes, and those planes are parallel to that line and thus that vector, and therefore these vectors are perpendicular to that vector. Right? So again, sort of, A connects to B, B connects to C, and so all together we know something about A and C. So the warning here is that not all of these, transitivities, I'm calling them, actually work, right? So don't be too fast and loose with your geometric arguments. So, for example, this vector here and this plane here are parallel, right? That said, that plane and this vector are parallel, and it's tempting to say if the first is parallel to the second and the second is parallel to the third, shouldn't that mean that the first is parallel to the third? But no, right? It really doesn't work. V and W not parallel. Pretty clear from the picture. Right, likewise, now let's look at one down here. Let's see here. These two planes, P and Q, are perpendicular. These two planes, Q and R, are perpendicular. But P and R, not perpendicular, not parallel. There's no relationship that we can conclude. Purple and green together tell us nothing about a speculated relationship between P and R. Everybody see the problem there? Right? So again, the warning that I put here is just think it through carefully if you're going to make one of these kind of transitivity arguments. Again, I suppose it would be possible to enumerate all possible such arguments and then document which ones are true and which ones are not true. But it'd be a very, very long list because there's perpendicularities and parallelnesses. There's also vectors and planes and lines, and it's too many different ways of conceivably fitting those together. So what I suggest for Math 219, let me rephrase that. The policy for Math 219 is you're perfectly welcome to make a valid transitivity argument. You don't have to prove it. You can do like I did here and say, well, these are perpendicular to that, that's parallel to this, and so, bam. If it's right. Right? So if your argument is valid, it's cool. Just watch out, because again, some of them that cosmetically, not looking at the geometry, just looking at how they show up on the page, right, could lead you astray if you're not careful. So always think about the geometry and kind of mull it and make sure that, sure enough, that definitely works before you use it. Okay. Everybody happy? All right. Okay, so how do we parameterize a plane? Keep in mind what we mean by parameterize. That means we want to make a point generator. And previously we've talked about parameterizing curves. And what we found is that one parameter, as that parameter changes, of course we think of that parameter as being time. As time changes, we kind of trace out the motion, position depends on time, and that literally traces out unavoidably a curve, right? So if we want to parameterize a plane, well, there's no way that a single parameter is going to do that. A single parameter is going to give us a curve. It's going to turn out that what we're going to need in order to trace out the entire plane is just two parameters. So let me make the case for this. Here's how this comes together. Let's suppose we know some starting point on the plane A, and suppose I have a vector V parallel to the plane, and suppose I have a vector W parallel to the plane. So how would I generate this point here, X? Some arbitrary other point on the plane. And now there's going to be a certain amount of a geometric appeal here. The idea is if you have the orange point and you want to generate the purple point, you're just going to kind of have to go some appropriate amount in the direction of the green V vector, and then after that some appropriate amount in the direction of the blue W vector. Now, how much will you go in the direction of the green vector? What are the odds that it's exactly the V vector? Unlikely, right? It's probably some multiple of the V vector. And then likewise, it's not going to be exactly the W vector. It'll be some multiple of the W vector. But if you have control over these parameters, S and T, you can go as far as you need to in the V direction, and then when you get to the right point, you can then go as far as you need to in the other direction, thus getting you where you want to be. Yeah?
Are V and W unit vectors?
No. Yeah, could be, but don't have to be.
Okay, so the S and T
are not distances.
They're just like scalar multiples of V and W.
Mm-hmm. Oh, well, they're just scalars, and then SV and TW are the scalar multiples.
Okay, so then if V and W were unit vectors, S and T would define the length of the size of the plane.
I'm going to say yes, and then I'm going to quibble. S and T can be negative, distances can't be, right? So S and T, if S were negative, for example, that would represent me just going this way.
Yeah.
So, there's this constant annoyance at the fact that distances have to be positive. The word distance means positive, right? And these scalars, S and T, don't have to be positive.
So technically that would just give a direct, like the negatives could give a direction, and the scalar value of the magnitude.
The absolute value, that's right. Yep, totally. So like I say, it was just a quibble. Yep, yes.
So can V and W just be any two non-parallel lines on a plane?
Vectors, but yeah, non-parallel vectors, yep, totally. Exactly. So there's a satisfying aspect of this altogether, which is, there we go. Notice it's two parameters, S and T. I need the flexibility of how much am I going to move in the V direction, and I need flexibility on how much I'm going to move in the W direction. But two parameters gives us a two-dimensional plane. And that kind of tracks, I mean, that's somewhat appealing that would work out. So, nice little formula to keep in mind, and a good one to have at your disposal. Just remember, that's how you parameterize a plane. Here's an example. Kind of familiar. We have previously seen the idea of defining a plane by 3 points. Right? There's going to be a unique plane that contains those 3 points. Now, if I wanted to parameterize this, well, referring back up to here, what I need is a point in the plane and two vectors parallel to the plane. Okay, well, let's see, a point in the plane. I'm flush in points in the plane. I've got 3 of them. Pick your favorite. It doesn't matter. Any one will do, right? I'm going to pick A for sort of alphabetical order reasons. Also, I like small numbers. Doesn't matter. So you have the point in the plane. How do you get the vectors parallel to the plane? Well, as previously discussed, pick one to subtract from the other 2. Again, I like the smaller numbers, so I'm going to pick A to subtract from B and C. And now I have 2 vectors parallel to the plane. I have a base point in the plane, and then here's my parameters that between the 2 of them complete my picture, complete my parameterization of that plane. All good? Okay. All right. Okay, distance problems. There's a bazillion of these. So again, let me remind you, do not think of this, please, as a list of formulas to memorize or a list of algorithms to memorize. Think of these as tools that, can solve specific questions, but which, as tools in your toolbox, might be useful in other circumstances as well, right? So anyway, here we're going to go through several of these examples. We're going to start with a given point and a given line. And how would I compute this distance from that given point to that given line? And there's again, various different ways that you can do this. What we're going to do here is we're going to argue that, if this line is parameterized, then I have x naught and I have v. That's what a parameterization of the line gives you, which allows me to compute, for example, this difference vector w and this projection vector that I have there in orange. Right now, that's just, given the x and the x naught and the v, I can write down the blue and the orange. And then you notice that what I'm actually interested in is the magnitude of this vector that is their difference. And then magnitude gives you the distance that you're interested in. So, clever little trick, right? And again, I didn't think of this. Somebody showed this to me long, long ago. So now I'm showing you, right? And so this is, a good tool for your toolbox. Keep in mind this idea. Projection might not actually be the thing that you want. Projection might be the thing you're trying to get rid of, right? This vector w, I don't want it to have a projection parallel to the line. I want the part perpendicular to the line. So fine, subtract off the part that's parallel. Right? Simple idea once you kind of see it. Okay. Now, same question. Different solution. Why do we need to have two different solutions to the same question? Because we're not interested in the question. We're interested in the tools. Right? And so this is a different tool for your toolbox that is useful in different circumstances. And again, who knows what's going to be useful when. All right, so now same setup. This is a weird approach, I will confess. I'm going to compute the distance by instead focusing on something I am actually not interested in. I'm going to focus on that area. Seems like a weird thing to want to do. It's not what I'm interested in. By the way, this big picture strategy comes up a lot in math, where if you're interested in one thing, find something else to compute twice. Where the thing that you're interested in is going to come up as part of one of those calculations. And having done that, the thing that you're interested in can be easily solved for because, of course, the two different answers that you got for the thing, you don't actually care about area in this. I don't really care about area. But the two different answers that I got have to be equal, and then you can just straight up solve for what you want. So it's a really clever strategy. I've seen this used in multiple areas of math. Very cool idea. There's a couple of other places in this course where that gets used as well. Yes?
Do you mind explaining?
Oh, yeah. Oh, I'm going to go through. I've got a lot more to say. Yeah, of course, yeah. I just wanted to hit the big picture first, and then we'll get into the details. Yeah. Okay, so that's the big picture. Now let's talk about the details. This first computation of area here, right? And again, it's this area of this parallelogram here. And high school geometry tells us that height times base. And of course that base, if you think about it, right, you look at the way this picture is drawn, that base, this distance, this orange distance here, is the magnitude of the projection vector. Which, by the way, I could have written as the component, absolute value of the component. I left it as projection because we had been talking about projection in the other approach. So, whatever. Okay, so height times base. Does everybody remember that one? Yeah, question?
Are the lines around the P that are magnitude?
Yep, absolutely. Yep. Okay, so height times base, that's one computation of area. Again, not interested in area, right? But nevertheless. Okay, now let's compute area a different way. Same area. And I think it's a pretty easy pitch that area. But being as it is a parallelogram, it's a cross product, magnitude of a cross product, that is, of the two edge vectors. It's a fact from last time. One of the cool things about cross products. This is assuming that this is a three-dimensional picture, by the way. Yeah.
I understand why, like, the cross product is the area of the square
Yeah.
or the rectangle, but how is D, like, the diagonal from a point to a point, the height of what you're trying to find? Or is it, am I just, like, looking at it wrong?
No, it is. I hear where you're coming from. Let me go back over to here. You got to keep in mind that we started off with a point and a line, right? And then I specifically decided, because I'm interested in that distance, I specifically decided to drop a perpendicular there. And yeah. That's when we say distance from a point to a line, we mean perpendicular distance, because there's a lot of distances, right? And which one of these represents the distance to the line? Well, the shortest one. And the shortest one is perpendicular. Does that make sense?
Yeah. So it is really just the base, which is you have x, which is your point that you're trying to find the area around. I guess that's that way.
Yeah, I know what you mean. Yeah.
And then x naught, so you create the vector w and then project it onto like your base.
Yeah, it's the same. This is the same projection that we did in the previous tool.
Okay.
Yeah, back here.
D is your height, where D is the perpendicular distance.
Yep.
Okay.
Yep. Is that cool? Everybody's happy? So again, two different computations of area, and we were actually interested in that distance. It's easily solved for, and there you go. So clever little move. I did not think of this myself, right? Somebody showed me. Now I'm showing you tools for your toolbox and all that. Okay. All right. Here's a clever one. The distance between two parallel planes. Now again, when we say distance, we mean the perpendicular distance. Because after all, if I just said pick any point in the one plane and any point in the other plane, I would probably get a greater distance, right, than that perpendicular distance. So the distance, the only reasonable choice for what is the distance is the shortest possible, or in this case, the perpendicular distance. So, all right. So what are we going to do about this? How are we going to compute that? Step one, pick any 2 points and subtract. And gives us this b minus a, which is not what we're interested in. But I can talk about, well, what is its component in the normal direction, right? If I have these two planes that I know they're normal vectors, and so the normal component of that is the distance that we're looking for. Is that cool? Yeah.
How do you find the magnitude of the distance? Like the direction is n, but like how are you to calculate the actual magnitude given plane A?
I guess I'm not following. So we have these two planes,
Yeah.
which means we have the normal vector.
Yes.
Pick any point A and any point B, and it doesn't matter, just any random point that's in the respective planes, and then just subtract them. Is that cool?
And then, okay, and then we basically just, okay.
Yeah.
I got it. Yeah.
Cool. All right, last example here. Distance between two skew lines. So now, skew lines, what we mean by skew is that they have nothing in common, roughly speaking. So they don't share a point and they don't share a direction. Okay, given these, basically unrelated lines, how would I find the distance between them? And again, really clever idea. I wish I thought of it. The big clever idea is that I can argue that those two lines have to be in parallel planes. And I know they are because I can find the common shared normal vector. If you think about it, what would I need of this normal vector? Well, I would need this normal vector to allow this plane to contain that line. I would need the same normal vector to allow this plane to contain that line. So I need this normal vector to be perpendicular to L1 and perpendicular to L2. So I can just take the given direction vectors and just cross them. The cross product of those two dark blue direction vectors gives us this needed normal vector for these parallel planes. That's a kind of a slick move. And now, who cares? We've identified parallel planes, so what? The goal was to find the distance between the lines, and the neat observation to make is, well, the distance between these two lines, and again, as usual, perpendicular distance, is also the distance between these two planes. And we already know how to compute the distance between two planes. There it is. Real clever move. Very slick. So again, the goal is not to know the answers to these specific questions. The goal is to understand how we used tools to create more sophisticated tools, basically. We're using subtractions and dot products and cross products and such to come up with clever ideas for how to relate these objects. Yeah?
Going back to the example from 2 examples ago,
Okay.
why exactly is the magnitude of the cross product of two vectors, how is that equal to the area of the parallel?
Oh, it's hard to see. That's one of the things that I skipped back in the section about cross products. Do you remember how I gave you a bunch of facts, but I absolved you all of all responsibility for the proofs?
Yeah.
Yeah, there's about a 10-minute conversation in there about going through basically that proof. So if you want to hear that conversation, I'm very happy to give it to you. Just come talk to me after class. I'll be happy to walk you through it.
So we just need to know it as a fact.
You need to know it as a fact. That's right. And it is a cool reason why, but you don't have to. Okay. All right. Okay, so that's 1.6. 1.5. That was 1.5. Moving on now to 1.7. Of course, we did 1.6 on the first day of class, so that's long since done. New coordinate systems. I think it's a good idea to start by looking at our usual coordinate system, aka rectangular coordinates. It's something that's familiar, I'm sure. The big idea is that if you have a point in the xy plane, there is a standard x coordinate and y coordinate defined by the usual picture. That gives you rectangular coordinates, and those coordinates are unique. Another little mathematician shorthand thing, exclamation points, very often used to represent something being unique. So there's a unique x, there is a unique y, and thus a unique set of rectangular coordinates. Okay, cool, obvious. But we're going to have to let go of it. And new coordinate systems that we're going to talk about, polar coordinates, cylindrical coordinates, spherical coordinates, they're not unique. It's weird that they're not unique, but they're not. So this is something that we, again, as much as we appreciate, as much as, let's say it this way, as much as we take this for granted in rectangular coordinates, we don't have that luxury going forward. Okay, another one, really easy to do what you might call algebra in rectangular coordinates, right? So you can view coordinates as coefficients if you're using standard basis vectors. In fact, technically, this is the definition of coordinates. Think back to linear algebra, right? Coordinates with respect to a basis, they are coefficients in a linear combination. Right? But anyway, question.
Again, going back.
Okay.
The one where there's two skew lines.
Yep.
And you're identifying Is there going to be any example in which there's two lines when you can't make parallel planes? Or
If
every two lines?
in fact, any two lines can be put into parallel planes. If the lines themselves even are the same line, then in fact the job just becomes all the easier. There are a lot of parallel planes, in identical planes, right?
Like if one's like this, one's like this, it's like parallel.
Well, by this rule here, whatever your two lines are. Let me get rid of all this junk. Whatever your two lines are, they have direction vectors. And you can cross them, and that will give you a direction perpendicular to both.
Okay. So
Yep.
it's the same as any two lines.
Any two lines. Yeah, the reason we made them skew here is so I wouldn't have to worry about various different cases, such as, well, what if the two directions are parallel? If they're parallel, the cross product's a zero vector, and so we have to do a different thing, which ends up actually being easier. But I just didn't want to deal with cases, basically. So skew means there's really only the one case to consider. Yep. All right. Yep.
For that problem, would the actual distance then be the length of egg? Or
Yeah. Oh no. It's the length of the component or the projection, or said differently, it's the component, the absolute value of the component.
Okay.
Yeah. Right. All right. Okay. So. Yeah, convenient algebra, linear combination of vectors has coordinates that are linear combinations of coordinates. It's just convenient, and again, something that we're accustomed to and something we're going to have to let go of. None of this works in non-rectangular coordinate systems. Okay, so we're going to start with polar. Some of y'all have probably seen polar coordinates before. Here's the picture, pretty much. So given a point that has rectangular coordinates, x and y, you can talk about by what angle could I rotate from the positive portion of the x-axis, going counterclockwise, to get to the direction that I'm interested in. And then next, loosely speaking, I'll clean up my mess in a second. How far do I need to go in that direction? Right, that's approximately, loosely speaking, what we're talking about. Little detail. I can't technically say how far. How far suggests a distance. Distances are intrinsically positive. R does not have to be positive. R can totally be negative. There's really no problem with it being negative. It's just that if it's negative, if you've got a theta that defines a distance, positive R's mean this way, and then negative R's just mean, well, just go backwards. Yep.
Are polar coordinates, are you able to define things outside of a two-dimensional system in polar coordinates?
I don't know what you mean. I'm sorry.
So, if I wanted to, think of it in, R3, and I wanted to...
Oh, yeah, no. Polar coordinates is specifically two-dimensional.
It can only be two-dimensional.
Only, strictly two-dimensional. Okay. There is a related coordinate system in 3 dimensions that we're going to talk about in a few minutes. Okay. Yep. Okay, so again, loosely speaking, apologies for the sloppiness, but theta tells you how far you sort of rotate around to get the direction, and then R tells you, roughly speaking, how far you go in that direction. And again, negative is allowed. So I like to think of these as being inputs to a function. So this, I've already forgotten the colors I used. Theta is a value, and this R is a value. And as such, you can think of there being a function that takes R and theta and then gives you x and y. And you can just write down a formula for x and y as functions of R and theta. It entirely comes off of this picture right here. Specifically, we think about this triangle, this right triangle right there, and a little bit of trig gives you this formula here. And I'm going to let you all think through the trig of that triangle. Here's your conversion formulas. X and y are functions of R and theta. All right. Is that cool? Yeah. Yep.
Does that mean we're restricted to what quadrant we can have? Because if it was over 180 degrees, then the R would still be positive, but the theta would be over.
There's no restrictions at all on either R or theta. R can be any value. I mean, theta can be okay, well, starting from the positive part of the x-axis, go around several times, right, and then end up that. Yeah, totally, no problem at all. And then once you have a direction, you can go as far as you want that way, or as far, with negative values of R, as far backwards from that direction. Is that cool? Yeah. And this is part of the problem with the uniqueness issue, and that segues very nicely into the next thing here. Here's several examples of the uniqueness problem we were talking about. This point right here, which I'm going to think of as having a certain angle, theta, that you can see right there. Well, if you were to just take an additional full turn, notice that additional full turn just gets you right back to pointing the exact same direction you had been. Right, so add 2 pi. You get a different set of coordinates. Now let's, by the way, let me fill out the rest of this. So that distance, I am just going to say, let's suppose that's 5. Then our first set of polar coordinates gives us that point. And then if you do the additional turn around, in other words, if you add 2 pi to theta, then now we have a different set of polar coordinates for the exact same point. Everybody okay with that? A little weird, but perfectly legal. Now here's another thing you can do. Instead of going a full turn around, what if you just do a half turn? just add just pi. That means that your angle is going to do like that. That's going to therefore have you pointing, let's see here, well, I'll just do it in the red. It has you pointing sort of that direction. Going that direction, how are we going to get to this original point? Well, just negative value of r. Remember, negative values of r just means go backwards. So, same point. Negative 5, negative value of r gives another point. That produces the exact same point in the xy plane. So there's, in some sense, kind of two different versions of polar coordinates. And obviously you can add 2 pi as many times as you want, right? But there's the one that has what you might call the positive value r, in other words, if you will, the correct direction. And then there's the one that has the negative value of r, namely the one that has what, if you will, sort of the exact wrong direction. But either one gets you there. Okay. All right, a couple of things to be worried about. Here we go. Let's be careful with your notation. A lot of people will write down like 2 comma pi over 6 and happily view that as being clear as to what you're talking about. And you may have thought that because maybe you figured, look, it's pretty clear that that's an angle, right? And if that's an angle, then doesn't it look like that must be the r for polar coordinates? And so presumably we mean this point. But the thing is, what you've got written down here, just if you write down only 2 comma pi over 6, pi over 6 looks like an angle, but there's nothing that actually says that it is. Pi over 6 is a perfectly legitimate real number. 2 is a perfectly legitimate real number, and these could be the rectangular coordinates, right, of a what is in fact a different point, and maybe it's that one. So these are different points. Which one do I mean by 2 comma pi over 6? That notation is a little bit ambiguous, just a little bit. Right? Easily resolved. If you want to remove the ambiguity, if you want to say, look, no, I didn't mean that. All you have to do to indicate that this is what you meant is just say so. R comma theta equals 2 comma pi over 6. Ambiguity gone. Right? No big deal. So just be careful with that. Make sure that that you, whenever you use polar coordinates, make sure that you don't accidentally write something down that could be either. Okay. All right. Here's a nasty little problem. This is dangerous. Students will get a lot of wrong answers because of this little problem here. Easy Pythagorean relationship from the triangle that we wrote down before. Another little trig relationship. All this is based on this picture. I'll draw it again. We have this picture here. That's r, and that's x, and that's y, and that's theta. Right? So easy relationships to write down. There is a temptation to write down r equals plus or minus the square root. And likewise to, I'm going to air quote and say solve. So, theta equals arctan. I'm going to deliberately leave those unfinished because they're not valid. Here's the big problem. Arctan is a perfectly well-defined function. Arctan of some value is one number. But theta isn't. There's a bunch of different polar coordinates. Theta that could be the polar coordinate that we need for the point in question. And likewise, this r equals plus minus. If you get right down to it, this notation's really sloppy. Does this mean that r is allowed to be either one of these values? Or maybe does this mean that r is one of these numbers? I just don't know which yet. Those are different. And we tend to use the same tragic sort of notation to represent both of these pretty different statements. So I think that's all bad. I discourage any of this. This is all a problem. So just leave it as we have here, and then don't try to find the polar coordinates by algebra. Don't forget to use the geometry. The geometry is what really solves the problem. So let me show you the trouble you can get into if you're a little careless. Here is a point, -1, -1, right there. And we can plug those values into here and into there and then there and there. And we could then, if we're, again, a little careless, we could say, okay, well then r has got to be square root of 2. And theta's got to be pi over 4. And oh man, I missed. Theta has got to be pi over 4. And you could look and if you just take an algebraic point of view, you could say, well, square root of 2, pi over 4, boom, and you move on to the next question. You don't even look back, and your answer is completely wrong, right? Because look at these numbers. Square root of 2 and pi over 4, well, pi over 4 is that direction, and square root of 2 in that direction would get you to here. And that's not the point that we're interested in. Everybody see what went wrong there? Look how easy these numbers were that generate an example where the algebraic approach is just wrong, right? So this is not some sort of obscure situation that, oh, don't worry, that'll never come up. No, this is a real, everyday kind of problem, right? So you really have to think through the geometry. Let me correct myself. I suppose you could document a set of cases and deal with it that way, but you're going to forget. It's going to be a lengthy list of cases. It's going to be completely unintuitive. You're going to get stuff wrong at some point. Maybe not even in this class, but at some point, right? I think it's much better to instead look at all your options. Let's see here. So, here we go. Let's look at all of our options for R. There's all of our options. Let's look at all of our options for theta. Well, there's a bunch of options for theta. There's kind of pi over 4 and 5 pi over 4, not to mention all of the 2 pi, full terms that you can throw in as well. And then think about the geometry. So, for example, I could understand this point as being in that direction by that amount. What is that direction? Well, it's 5 pi over 4. How far am I going in that direction? Well, square root of 2. And notice now I've got a set of polar coordinates. Square root of 2 and 5 pi over 4. That gets me to the point I'm interested in. Yeah.
So is there no definite quadrant in which r is positive or negative? Like you just
r can be positive or negative in any coordinate, in any quadrant. Sorry.
So you first find out the direction of theta, and then if r is positive, it's in the same direction.
You don't have to do the theta first. You've got a bunch of options. I'm just saying you have to think it through, right? I tend to like to do the direction first, sure, but you don't have to. Let me show you the other way to do this point here. Right, so the other option here, let's see here, my other option, I can think of this exact same point. Oh man. Okay. Oh, this right here? That's Latin. It means nota bene. It's like FYI and EG and stuff like that. It's just it heads up basically.
So it means FYI.
It's similar. No, I'm just saying it's one of these. It's a common English abbreviation. So it means nota bene, which means something to the effect of heads up. Here's an important point. Yeah, that's all.
Like be aware.
Something like that. Yeah. Right. Okay, so here's the other way you can do it. Let's take my other direction. Pi over 4, that's the other direction. Now, can I get to this orange point by going in this red direction here? Well, yeah, sure, just I'd have to go backwards. I would have to go negative pi over 2 to get to that orange point. Right? So notice it's not hard to think through the geometry. Thinking through the geometry will save you getting wrong answers, right? Or save you having to deal with a list of cases that you memorize by rote that you will eventually forget. So I'm a big believer in looking at the picture. And I think we're out of time now, so we'll draw the line right there. We will pick up here on Monday. Y'all have a great weekend.